Welcome, welcome, welcome. Make sure everything's going here. All right, is it time? Yeah, it's time. It's 1:10. Thanks for showing me. All right, let's pin my video here. There we go. All right, I'm all good. All right, so let's do this. Cool. This is kind of far back. All right, one sec. All right. Where do you guys want to start? I got some ideas, but if you have questions, happy to hear them.
Could we continue on the example that you were doing before last week?
Totally. So I don't remember exactly the numbers I was using, but we will do the same sort of thing with maybe slightly different numbers. Yeah. So I was kind of leading up to why the directional derivative is calculated the way it is. Now, you probably don't have to absolutely know this. Like eventually it's going to be fine just to know that to calculate the directional derivative, so that's the derivative in the direction of u of the function f. We don't always write the little arrow above the u there, but I like to write it because u is a vector. That's always going to be calculated by doing the gradient of f dotted with the, oops, that's not right, dotted with the unit vector in the direction of u. So usually we use the letter u because it's already a unit vector, but if it's not a unit vector, the way you make a vector be a unit vector and still have the same direction is just to divide it by its own magnitude. Some people use this symbol, some people use the double symbol like that to mean magnitude, same difference. So the vector I'm going to use in this example, I'm going to say u is the vector. And again, there's like 3 or 4 different notations for vectors. I prefer to use the vertical bracket notation for my vectors. That is how I like to write a vector with 2 components. So I'm going to make u the vector 3, 4. But other people might write this like this, right? People might write u equal to, they might write it with brackets like that. They might write it using parentheses and a comma. They might write it using brackets that are angled like this. So just be aware, there's lots of different notations that can mean a vector. I feel like this is probably the worst choice because we also use this notation for like coordinate pairs. I think this is the choice that some of your professors happen to be making. Sorry. So anyway, so the example we were looking at last time was we have, my favorite function, f of xy equal to 9 minus x squared minus y squared. And we were at the point, I don't remember if it was 1, 2, 4 or 2, 1, 4. I'm going to say 1, 2, 4. No, I'm going to say 2, 1, 4. So basically, here we are. And here's my coordinate system. And so again, I'm thinking of this as like a mountain where the top of the mountain is at the point 0, 0, 9. So this point here is 0, 0, 9. And for lack of a better word, if you're at the ground or if it's like sea level, like over here, here's the point 0, 3, 0. Here's the point 3, 0, 0. And these also extend in the other direction. Like this. Whoops, that's not as good as it should. Sorry. The circles don't always come out great. Sure, perfect. Okay, so there's our coordinate system. And we are saying, all right, if I go over to the point 2, 1, 4, so 2 in the x direction, 1 in the y direction, and 4 in the z direction. So really, it's going to be up here. So this is the level curve z equal to 4. Now at the point 2, 1, 4, so I'm like right there. At the point 2, 1, 4. The question I'm trying to ask and then answer is, what's my slope of either ascent or descent if I travel in the direction 3, 4? Meaning, from this point, I'm traveling 3, now this is going to be hard for me to do, I'm traveling 3 in the x direction and 4 in the y direction. It's easier if I just draw it in the plane. So I'm going to take my this red circle here. I'm going to try and do a decent job of drawing. So this circle with z equal to 4, that's going to be a circle of radius square root of 5. Because if I set z equal to 4, here's my level curve. If z equals 4, I've got 4 equal to 9 minus x squared minus y squared. And solving for x squared plus y squared, I get x squared plus y squared equal to 5. Which means it's a circle of radius square root of 5. So try and draw this well here. I'm going to go over, out 2, and up 1. So my circle is going to look kind of like this. And I'm over here at the point 2, 1, 4. Right, so there's x equals 2. Actually draw it. X is 2 and y is equal to 1. Can you guys see that all right? Can I move the board closer? I can move the board closer. That's a little better. Oh. Sorry, just 1 second. I need to move the carpet closer because I don't want to get the black dust all over the floor. Oh. 1 sec. Okay, so.
James?
Yeah.
What does the point say? Is that
2, 1.
2, 1? Thank you.
Yeah, I can see that it wasn't easy to see there. Okay, so here's the idea. We're at this point, right, which is the same as this point, and we are traveling in the 3, 4 direction. Or if we normalize that or unitize that vector, right, the magnitude of u is just the square root of 3 squared plus 4 squared, which is just 5. So the unit vector that's in the same direction is this vector divided by 5, meaning u divided by the magnitude of u. If I divide this vector by 5, I'm just dividing each component by 5. It's the vector 3/5, 4/5. So I'm asking, what's the slope of the surface going to be, this surface over here, when I travel in the direction over 3/5 and up 4/5? That's going to look kind of like, I don't know. If I travel in the direction of u. Well, first of all, if I travel outward from the center, am I going up the hill or am I going down the hill?
Isn't it?
Definitely down. And so if I'm going down the hill, my derivative, aka my slope, should be negative. Or as we usually call it, like the steepness should be negative. So how do we calculate this? Well, I'm going to do something kind of funky, which is more of a 21C thing, but I think it helps kind of see what's happening here. So I'm probably going to go to the other side board. We'll come back and look at this. So here's what I want to do. Actually, I got enough room here. I can erase this and back this stuff here. So here's what I want to do. I want to find the derivative in this direction of this function. What I'm going to do is I'm going to parameterize the line that we're going in the direction of. So this is something I know we don't typically do, but it's not too hard to see what's happening here. Just bear with me for a minute. So this line goes to the point 2, 1, and has a slope of over 3/5, up 4/5. So here's how I would write it. X as a function of t is the x coordinate, which is 2, plus 3/5 times t. And y as a function of t is the y coordinate, which is 1, plus the amount we're going in the y direction, 4/5 times t. So here's what that tells us. When t equals 0, x of 0 is 2, y of 0 is 1. I just get the point 2, 1. And then if t was, say, 1, x would be 2 plus 3/5, and y would be 1 plus 4/5. So letting t equal 1 would move me over 3/5 and up 4/5, which is exactly the direction I want to be going in. And then letting t equal 2 would move me over another 3/5 and up 4/5 to be in the same direction. And t equals 3 and t equals 4 would keep moving me in the same direction of travel. So this is a way of parameterizing this vector, or actually the line the vector's on. Okay, so why am I doing this? Well, because now I'm going to find the derivative of this function as a function of t. Now check this out. I think I can squeeze this in here. So I did an example like this last time where we said, oh, yeah, sorry, I know this is going to be a little complex here. I know that my function is a function of x and y, but x and y are both functions of t. So if I want to find df dt, it's all the paths to get to t, meaning it's del f del x times del or dx dt plus del f del y times del y dy dt. Okay, but check this out, and this is kind of the cool part. You guys ready? Let me double check my notes to make sure I'm not going to screw this up. So I've written this down before. I want to make sure I get it right. Where'd you go? On the front page here. Yeah. Yeah, totally. Okay, cool. So look at this. Gross. Pat on my hands. Okay, so I can rewrite this as a dot product. And this is kind of the important part, so you really want to pay attention here. This is going to be the dot product of the vector del f del x, comma del f del y. That's just the gradient, right? It's the partials of f and y dotted with dx dt, dy dt. But dx dt is 3/5, right? If I look at the derivative of this function with respect to t, it's just 3/5. And dy dt is just 4/5. So what I actually end up getting here, I know again I'm kind of squeezed in here, I'm getting the gradient of the function f, which sometimes we write with an arrow above it to remind us of the vector, either way, dotted with the vector that's the u vector that's been normalized. So I want to say this again really, really clearly. We did this thing where we said, I'm going to let x be a function of t. And then we just found the derivative of f with respect to t in the usual kind of way. And we exactly ended up getting the thing we said was going to be the directional derivative. The gradient of f dotted with the direction that we are traveling in. And so this is the formula for the directional derivative. It's great. Now, to answer the question for this specific example, so in this example, our gradient, I know I just erased the function, but I know what it is. Our gradient is negative 2x and negative 2y. I'm just taking the derivative of f, right, with respect to x and y respectively, dotted with that vector there, 3/5, 4/5, which gives me negative 2 times 3/5, sorry, negative 2x times 3/5 is negative 6/5 fifths x. This times that is minus 8/5 y. I seem to be forgetting something here, which is that I have to actually plug in the point that I'm at, right? This here would give me the directional derivative at any point on the surface. To find the directional derivative at this point here, I actually have to plug in. So usually we end up plugging in, the point we've got, which is x equal to 2 and y equal to 1. So we end up, if I plug in 2 for x and 1 for y, we get negative 6/5 minus 8/5 times 2. Sorry, I know it's a little sloppy here. That's going to be negative 6 minus 16, so negative 22/5. So what that tells me is the slope going downwards is a slope of negative 22/5, meaning for every 1 unit I move outwards, or I move in the direction of u, I'm going down 22/5 in the z direction. Okay, so that's the example I want to point out. Now, you don't really have to know any of this, to be perfectly honest, but except for you do need to know, as I'm going to turn the board here, the thing you're going to want to know about directional derivatives is the following. The directional derivative of the function f in the direction of u is exactly the gradient of f dotted with. So people think of it different ways. I think of it this way. Like that. Some people say you just should normalize u first. So some people say, now this is how you should remember it. That's what I'm going to say.
Thanks.
Yeah.
When you were explaining the answer for the last part, I got the part you said that when you go in the z direction, you go down 22 units over 5 units.
Yes. Well, so the way I'm thinking about this is, so let's go back. Actually, let's go back to two-dimensional calculus for just 1 second. Let's pretend something super simple, like f of x equal to x squared. I wanted to find the derivative at, say, 3. So here's the point, 3 comma 9, and the derivative, aka the slope of the tangent line, f prime of 3 is, well, the derivative is 2x, evaluated at 3 is going to be 6, right? So here this means that the function increases by 6 for every 1 that my input changes. So right here, if x increases by 1, the y value increases by 6.
Okay.
Whereas over here, the idea is that if my input increases by 1, so basically if I move 1 in the direction of this vector, right, if I move out a whole 1, which is this much here, I'm going to go down 22/5. So from here, so like if I move, so I'm going to try and draw, it's probably going to suck. If I move out this way, I would end up coming down along the surface, and since I'm at a height of 4 here, and I'm subtracting 22/5, which is a little bit more than 4, right? It's 4.4 actually. I would end up just a little bit below the xy plane. So if I go out 1, I'm going to go down that much there.
Okay.
That's what the slope is at that point in that direction. If I moved like more to the left, it would probably be less steep. Okay.
So how do you write that in terms of qualifying the x and y?
So it's not really x and y, unfortunately. It's actually in the direction of u. So you could say the direction is just the unit vector. You could also say the direction. So if you move simultaneously 3/5 in the x direction and 4/5 in the y direction, then you'll be moving down negative 22/5 in the z direction. Now I should point out one more thing, right? This is an instantaneous rate of change, right? If you actually move a little bit, right, like that's what the slope is right there. Just like over here, right? At this point here, if I was thinking about moving 1 over, I would move 6 up. But then if I actually move over, then the slope gets steeper. So it's only at that point. But I mean, usually you're just asked to calculate this quantity. So you're like, oh yeah, the directional derivative of the function in the direction of u is this. let's do an example with it without all the graphic stuff. So where are my examples here? Oh shoot, sorry, accidentally. My computer went to sleep for a second. Let's see, I had a good example. Yeah, cool. So, yeah, let's do this one. So, first question, find the directional derivative of, where do we go here? F of xy equal to x squared y cubed at the point 2, -1 in the direction u equal to, say, I'm trying to pick different numbers here, 3, 7. All right, so this isn't too terrible once we get familiar with the stuff. So we have to find a couple things. We have to find the gradient, and specifically we actually find the gradient at the points. So really it's right, the derivative in the direction u of the function f at a specific point, x naught, y naught. So we're actually evaluating the gradient at the point x naught, y naught. So here, our function is x squared y cubed. Our point x naught, y naught is 2, -1. And our vector u is 3, 7. So let's find the gradient. The gradient is just the partial derivatives. So it's the partial with respect to x, which is going to be 2x y cubed. And it's the partial with respect to y, which is going to be x squared times 3y squared. I would probably write it as 3x squared y squared. But then we want to actually evaluate this at the point 2, -1. So let me just plug into a -1 for x and y. Plug into the top part here, we get 2 times 2 times -1 cubed, which is -4. Plug into the bottom part here, we get 3 times 4 times 1, which is 12. Okay. So then, to answer the question, the directional derivative is going to be this gradient dotted with this vector normalized or divided by its own magnitude. So it's going to be -4, 12 dotted with the vector 3, 7, but divided by the magnitude of this vector, which is just right, we usually write the division as just multiplying by 1 over the square root of whatever. So calculating this, I end up with, let's see, -12, right? -4 times 3 is -12, plus 7 times 12, which is 84. So -12 plus 84 is 72. So I get 72 divided by the square root of 49 plus 9 is 58. And that would be the slope of the surface in the direction of this vector. Meaning if you move in this direction, from this point, you're going to be going up at a steepness of 72 over the square root of 58, which is probably close to 10, maybe a little bit smaller than 10. I mean, I don't know, we can use a calculator, right? It doesn't really matter what the number is, but let's figure it out. Let's do 72 divided by second square root of 58. Okay. That's, I forgot my division symbol. I did multiplication accidentally. 72 divided by the square root of 58. That's going to be about 9.5. So yeah, close to 10. And so again, that tells us if we move in this direction, we're going to be going up the hill at a steepness of 10 units up for every 1 unit over, which is really steep. Okay, Questions? I do have let me give you a slight variation on this problem because there's another way people like to ask this question that's a tiny bit different that I always get mixed up with. So let's say I have the same question. And I've definitely seen this come up on either web work or WebAssign where it's asked this different way. It means something just slightly different and it's easy to not catch it if you're not paying attention. So another way we could ask this question would be, so again, find the direction. So find the directional derivative of the same function at the same point. We can call P usually. Now here's the different part. It's going to be in the direction of the other point, this other point Q, which is 6, 2. And so here's what I want to really stress. The direction we're traveling in is not the direction 6, 2. Because we're not starting at the origin. Right? If we started at the origin and we're ending up at the point 6, 2, then our vector would just be 6, 2. Because we go from our beginning to our end over 6, 2. But we're not starting at 0, we're starting at at 2, -1. And so the direction we're actually traveling from P to Q, well, those are different vectors. They have different magnitudes, they have different directions. And so the way we find this vector, that we often write like this, starting at P and ending at Q, is by doing the coordinates of Q minus the corresponding coordinates of P. So 6 minus 2 is 4. And 2 minus -1 is 3. So that's actually the vector, the direction we're traveling in. All right, so now that you guys know what direction we're in, I want you to go ahead and calculate the directional derivative. So I want you to find the directional derivative where, again, that's the gradient, which is just the partials evaluated at 2, -1. And U is the direction you're traveling in, but it's divided by the magnitude, right? So this isn't actually U, or if it is, I'll just do this, right? I'm right there. There, that's better. Divided by the magnitude. So I want you to calculate that. I'm going to give you a second. I won't lie, I'm going to use the restroom real quick. You guys do that, I'll be right back. Okay. Yes, I wash my hands. All right. So the way we're going to do this is the way we were doing it. So again, the gradient of f That's just going to be the partials in order, always x before y. Or if it's a function of 3 variables, fx, then fy, then it's z. Right? Sometimes it's more than 2 variables. So we're going to have the partials, which are again, is that already a different function? I did. All right, no big deal. Doesn't matter if it's a different function. So the partial here is actually 3x squared y squared. The partial here is actually x cubed times 2y. So 2x cubed y. Evaluated at, what is it? The point 2, -1. Dotted with the vector u divided by its own magnitude, which is just 4, 3. And the magnitude of 4, 3, you're going to see it a lot. The magnitude's 5. So we're just dividing by 5 here. So what do we end up getting here? I'm going to plug in some numbers. End up with 3 times 4 times 1 is 12. 2 times 8 times -1 is -16. Times, I don't like to divide by this until I have to, so I would just do this. And then 12 times 4 is 4. Interesting. So the reason I laugh is because this is going to end up being 0. So I get 12 times 4, which is 48, minus 16 times 3, which is 48, divided by 5, which is 0. So here's what that means. This is actually somewhat interesting. It means that on this surface, at this point, if you were to travel in this direction, you would actually be staying at the same height, right? You would be on one of the level curves where you don't change the z value. So if you get a derivative that's 0, right, just like in 2 dimensions, if your derivative is 0, it means you have like a maximum or a minimum because you've topped out, and the tangent line has a horizontal tangent line, and the slope is 0. Same kind of idea here. This means that if you're traveling in this direction from this point, you're going to be staying at the same height on your mountain. Right? So it's kind of like if you didn't want to go up or down the mountain, you just wanted to walk around and circle it, that's what it would be. Okay. You guys want to do one more? I see some yeses. Okay. All right, let's do it. Okay. So let's see where we're at here. Yeah. So for the function f of x, y equal to, what do I got here? Oh, sorry. X squared plus 3xy minus 4y squared. Find the directional derivative from the point p equal to 2, 1 in the direction of q equal to, let's make it, interesting, 3, 3. Okay. So go ahead and do the calculations there. I'll give you guys a minute. Also, in case anyone didn't get to it yet, there's the link to the attendance again. Okay, it's hard for me to wait. So sorry if you haven't gotten through it yet, but I'm gonna keep going because I can't just stand here and not talk. So again, the gradient, just the partials with respect to x and y, evaluating the point. I'm going to get, right, my derivative here with respect to x is 2x plus 3y plus 0. With respect to y, it's 0 plus 3x minus 8y. Plugged in my points 2 and 1 and got 7 and negative 2. And then my vector u is just the q's minus the p's. So it's going to be 3 minus 2, 3 minus 1. Okay, so then to find my directional derivative, it's going to be, again, this vector dotted with that vector divided by the magnitude of this vector, which is 1 over the square root of 1 squared plus 2 squared, which is 5. This is looking like 7 times 1 plus negative 2 times 2, all over the square root of 5, so 3 over root 5. Again, whenever you're finding a directional derivative at a point, you should always be just getting a number, right? You shouldn't get a vector as your answer, you should get some value. Because again, the value is representing the slope of the surface. Okay. A question people often like to ask about this sort of thing is, what's the direction of steepest ascent? Meaning, if I was traveling along this, well, I should say, if I was at this point on this surface, what direction would I need to travel in to go up the fastest or down the fastest? So I'm going to erase some of this, but not all of it. I shouldn't erase those at all. So the question we want to answer is, what is the direction from this point that ascends most steeply? Which is the dumbest way I probably ever said it. We usually say, what's the direction of steepest ascent? And to do this, it actually kind of requires us to remember something about the dot product. So if you recall, right, well, I mean, no surprise here, we're calculating this. The gradient dotted with this vector u. Now, sorry, u divided by the magnitude of u. Apologies. But we don't actually know what u is in this particular example. We're trying to figure out what is the vector u that's going to be in the direction that's steepest. So, how do I want to say this? So here's the thing we should have learned in 17B. Yeah, we definitely talked about this in calculus. If you dot two vectors together, one way of dotting them together, the easy way of calculating their dot product, is to just multiply the components together and add the results. Right? What we've been doing this whole time today, right? But there's another way of calculating the dot product. The dot product is more geometrically thought of as the magnitude of the vector v times the magnitude of the vector w times cosine of the angle between them. Now, the magnitude of v and the magnitude of w aren't changing, right? If you've got two vectors, their magnitudes aren't going to change. But if you want to kind of maximize this product, well, especially here, right? this vector's magnitude is definitely not changing, right? This kind of is, and this is going to be a unit vector with a magnitude of 1. And when you divide a vector by its magnitude is 1. So this magnitude isn't changing regardless of what this vector is, right? This is always going to be a unit vector. So if the only thing that is really kind of changeable is cosine of theta, or really the angle theta, what's the angle that makes cosine the biggest? That's a good question. Let me ask a different question. What's the biggest value cosine of theta can have? Yeah, exactly, 1. Okay, where on the unit circle is cosine equal to 1? Yeah. Okay, so if the angle between two vectors is 0, it means those vectors actually lie in the same direction. So here's what this actually means for us. For the gradient and the vector to have the same direction, this vector has to exactly be in the direction of the gradient. So to maximize the directional derivative, we want u to be the vector. Sorry, I forgot. Right, I forgot my. We want u to just be the gradient vector divided by its own magnitude, of course, so that it is a unit vector. And again, I know I said this a couple classes ago. If someone's ever asking you what direction is something happening in, even if they're not saying it, they want your answer to be a unit vector. So if your answer, like if my answer for the direction was like, 5, 12, my real answer should be 5, 12 divided by the magnitude of that vector, which is 13. Okay, so yeah, I got one here. So to answer the question here, the direction is, well, let's find the gradient. I already found the gradient, but I'm going to find it again. The gradient at this point, 2, 1, is just the partials. I think it was 7, 2. I don't remember that. 2x plus 3y and 3x minus 8y. Evaluated at 2, 1. So I get 7 and -2. Yeah. And so then my answer here would be that u is this vector, 7, -2, divided by the magnitude of that vector, which is the square root of 49 plus 4 is 53. So this would be the direction of steepest ascent. And that is always true. The gradient vector always tells you the direction of steepest ascent. And now I want to know, because sometimes they ask this question kind of the reverse way. Instead, they say, well, maybe I'm a skier and I want to get downhill as fast as possible. What's the direction of steepest descent? Well, if going that way is going to go up the hill fastest, turn around. And going the opposite negative direction is the direction of steepest descent. So to get the direction of steepest descent, you just slap a minus sign on the whole thing. So there is your steepest descent. The steepest descent direction is always the negative of the gradient. And so this actually leads to something moderately interesting, I think. Yeah, I want the other side of this. I guess I can just put this up here.
So for the, why did you use the 2, 1?
So that's the point I was starting at, right? So let me back up. It's the direction of steepest ascent. So if I'm on this surface at this point, right? The direction of steepest ascent is that direction right there. But if I was starting from a different point, the curve might be totally right, different looking. So, yeah. Let's see. Another thing worth noting here is that what's the steepest slope from this point? Well, that should be easy to calculate now that we know the following. We know how to calculate slope. It's just the directional derivative. And we know that the direction of steepest ascent is the direction of the gradient. So I'm going to try and find this directional derivative. It's actually going to be, well, my vector u there actually is the gradient vector. But normalized. That's what we get to use for u if you're finding the amount of steepest descent. So check this out. Look what happens. Using my formula, which oh yeah, it's right there, right? The formula for the gradient of f is just, sorry, the formula for the directional derivative in the direction of u of the function f is the gradient of f dotted with the vector u divided by its own magnitude. So here's the vector u divided by its own magnitude. I feel like there's something I need to say here that I'm forgetting to say. No, that's fine. So when you dot a vector with itself, you get the magnitude squared. Let me show you a real example. I'll come back to that. Don't worry. It's not going away forever. What's the magnitude? I know I've asked this like 10 times already. Here's a vector, 3, 4. What's the magnitude of that vector? Well, it's the square root of 3 squared plus 4 squared. 5. Okay, but what if you dot this vector? Let's call it v for a second. If you dot v with itself, that's 3, 4 dotted with 3, 4. 3 times 3 is 9. 4, but here's the thing. When you dot a vector with itself, you're exactly squaring each of the components and adding it together. You're just not square rooting it like you would in the magnitude. So when you dot a vector with itself, it's exactly equal to the magnitude squared. Does that seem all right? Cool. So here's the thing. When I'm dotting this vector with itself, I'm just getting the magnitude squared. So I'm getting the magnitude of the gradient, sorry, squared divided by the magnitude of the gradient. But one of those cancels, and you just get the magnitude of the gradient. Sorry, I'm getting a little sloppy there. So here's the very short answer to a long question. What's the steepest slope from that point? It's whatever the magnitude of the gradient is at that point. So you don't have to do all this directional derivative stuff to answer that particular question. You can just say, in this case, oh, well, I know that the gradient was equal to, I know I found it like 100 times. There it is right there. It's 7, -2. So the magnitude of the gradient is equal to the square root of 7 squared plus -2 squared, which is the square root of 53. And that is the steepest the slope can possibly be from the point 1, 2. And that's always true. If you're ever being asked, oh, what's the steepest slope I can get from a certain point? It's the gradient, it's the magnitude of the gradient at that point. If you ever ask what direction is the direction of steepest descent, it is the direction of the gradient. I wanted to talk about maxes and mins, but I think we've run out of time. So Wednesday, my plan at least, I mean, obviously, if you guys have questions, ask them. If you want me to make a video or two, let me know. But my plan for Wednesday is to start talking about finding maxes and mins and saddle points of three-dimensional surfaces, which definitely has to do with, so we're gonna have to use the first and second partials and the mixed partial to do that. But it's gonna be very much like in Calc 1, where you found a critical point by taking the derivative of something, setting it equal to 0, finding the critical values, and then testing those to see if they're maxes or mins. Just that the testing process is a little bit different when it's a surface as opposed to just a function. All right, that's all I have. So if you have questions, let me know, start a discussion, and make sure you fill out the attendance. Thank you so much. I'll see you guys later. Bye, take care. Yeah, I can end the meeting, sure. Bye.